Hello and welcome to another LeetCode problem. We are looking at an easy one. The purpose is that we want to practice the interview process and we want to focus on communication and a systematic approach. Picking an easy problem helps with that because the chance of getting stuck trying to solve a medium or difficult problem is much lower. So we'll be focusing on communication, the proper approach. We will try to reason about what we're doing while we're doing it to make it easy for the interviewer to follow what is going on in our head. And yeah, without further ado, let's dive into this. I haven't tried this myself. I haven't seen this problem before. Let's dig into it. So LeetCode 3258, count substrings that satisfy K constraint. And it's version 1 of that problem. So I guess there's a more difficult one that builds on top of that, but I'm not aware which one that is. But anyway, so let's read the problem description to get an idea of what we're dealing with here. So we are given a binary string S and an integer K. A binary string satisfies the K constraint if either of the following conditions hold. The number of zeros in the string is at most K. The number of ones in the string is at most K. So one of these two conditions must hold. And then we can say the K constraint is satisfied. Return an integer denoting the number of substrings of S that satisfy the K constraint. Okay, interesting. And what are the constraints on the input? So the string contains only zeros and ones. The string has at least one character, nice. And our K is at least 1. Okay, cool. So we don't have to deal with edge cases. So that's where we have to take care of empty strings, etc. For our runtime analysis, we're just going to ignore the fact that the length of the string is bounded. Otherwise, everything is automatically constant space and constant time. So yeah, we'll just pretend that the string is of arbitrary length or of length n. Now let's dig into some of the examples to understand what's going on here. Okay, so here we have the input string consisting of zeros and ones. Just 0, 1, 1, no, 1, 0, 1, 0, 1. And K is 1. So that means we are looking for the number of substrings where the number of zeros and ones is at most 1. So if I go here, so this would be, well, every single character is a valid substring, right? So we'd have 5. Then this is a valid substring. This isn't, but this is also a valid substring. So we now have 5, 6, 7, 8, 9 valid substrings. And then we have valid substring of length 3. So this would be 10, 11, 12. And this is a valid substring because the number of zeros is at most ones, even though the number of ones is larger. It doesn't matter. Only one of those constraints has to be satisfied. Okay. And then when we, okay, so this is the same example, what we're adding 0, 1, and then the number almost doubles. Okay, well, that is because the number of valid substring of length 1, of length 2, and length 3, and length, etc. has increased. That's why. And here's another example. This has only ones, K is 1, so, okay, of course, only substrings of length 1 are, oh, because there are no substrings that contain 0, all substrings are valid. So that's an interesting one. So how do we get to 15 if we do that? So 1, this is a valid 1, 2, 3, 4, 5. Yeah, I'm thinking about a sliding window approach, but I'm not sure how to get to 15 with a sliding window approach. The naive approach would just be to try all of the different substrings at different lengths out and see if that works, right? That would be, what would be O of n, well, we'd have to inner loop and an outer loop. That would be O of n squared and O of n space. And a sliding window approach would probably only use O of n time and O of n space. or even constant space. But yeah, by the way, good practice for an interview. If you see one solution, don't try to find a better one if you can't right away. Just implement maybe a brute force one. So we're just going to implement the brute force one of n time and O of, well, I don't think we need, well, actually, we probably need n space as well. So this is going to be the brute force one. We will iterate over all of the possible substrings, and we will have an outer loop and an inner loop. So the inner loop will be about over the length of the string, and the outer loop will be over the start of the string, right? For I in range length of the string S. Yes, and then we iterate for j in range I to the length of S. And we have to check whether the constraint is still satisfied or not at this place. So the substring will be, well, S from position I to position j plus 1. And now we have to check if it's a valid substring, right? Maybe just do it like this, is valid substring. Then our counter is increased. Otherwise, we're going to break out of the loop, because if we increase the length of the string, it's not going to make the string valid again, right? Counter equals 0, and we make a little helper function. This is also good practice, by the way, to modularize the code a tiny little bit, but don't go overboard with it. At valid substring, and we do a string S, and we return a bool. And by the way, in an interview, you likely don't have to do any type annotations at all. I'm just doing that because it makes it look nicer. So we're going to count the number of zeros and ones, and we're going to use a little counter array. And then we're going to do for I in range length of S. And we're going to say counter at index. We're going to increase that at the index. We're going to say index is equal to 1 if S as position I is equal to 1. Otherwise, it's going to be 0, because we know that there are only zeros and ones in our input string. And else it's going to be 0. There's also another nice way how you can write that. And that is just by doing this and that. So you can use actually a Boolean evaluation as an index. So this will be true if the character position I of the substring S is 1. And if it's true, then this one gets selected here. And we can make that even simpler and just put that in here. Yeah, directly like so. So, and yeah. And then we simply perform a little check. If the maximum of any of the counters is larger than k, we're going to return false immediately. Right? Because that means, no, wait, if the minimum is larger than k, because one of the two could still be smaller than k. As long as the smaller one of the two is smaller than k, we're good. We're still satisfying one of the two conditions, and that satisfies the k constraint. Right, and yeah, return counter. I think that's it. I'm just going to run this. That worked. Let's submit it to see if it passes all of the test cases. And then we'll have a look at maybe an optimization. Okay, so we don't care, by the way, about the runtime. We only care about the asymptotic. The LeetCode runtime changes every time you submit your solution. So 392 milliseconds, if I run it again, 381 milliseconds. So, and by the way, if I submit this in the middle of the night when nobody's using LeetCode, the times get faster even more. So yeah, it's useless to look at those runtimes really. At least when you're trying to use LeetCode for interview preparation. Okay, so yeah, so now we have one solution and O of n space. That is because we built the substring. We could also reduce this to O of 1 space, by the way. And let's just do this real quick. Instead of passing in the entire substring, all we do is we just pass in the indices of the substring, and left, right, and we're just gonna take them as the int values. And all we do now is we iterate over this range. And this should work the same way. Yes, and I submit that. Yeah, so it still works. So now we've reduced the space complexity, but there's also a way, I think, to reduce this to a linear time and constant space as well. So, but let's start with linear time and linear space. So what we could use is a sliding window, I suppose. A sliding window. Now, this is difficult to see by yourself, but there exists a pattern in LeetCode problems that exactly deals with this. You know, how many substrings do you have in your current sliding window? And there's actually a nice formula. And you will find it when you look at some of the other solutions, I suppose. I will just show this to you. This is something you should probably just remember. That's all you have to do. So what we will do is we will have our counter that counts our zeros and our ones. And that will tell us when we need to, contract our window. And we'll have a left pointer and we will have a right pointer. And what we'll do is while right is smaller than the length of the string s, we will perform the following. We will increase our counter at the index. And remember, I deleted the code now, but let me see if I can get it together again. So we're going to take the character at position right. So we're going to say s at position right is equal to 1, right? And if it's 0, then we increase counter at index 0. Otherwise, we do the same. And later, to contract our window, we're going to do this. So we're going to actually decrease the counter, but we're going to use it on the left index. So we will need this in a second. Okay, so that's what we do. And now we do if the minimum of our counters if the minimum of our counters is larger than k, well, while that is the case, we know we need to contract. And if that is not the case, we need to update our result. How about I get this right now from memory? So we can use the left and the right pointer to calculate how many valid substrings are in the current valid substring. So every time we encounter a character, we increase our result, and we add however many elements are currently in our valid substring. I think that's how it goes. I'm not 100% sure. So this is also a good exercise for me. And if I get it wrong, we'll have a look at some other people's solution. I'm sure we'll find it there. So the result is equal to the length of the current valid sliding window. And the length is nothing but the right minus the left. But if right and left point to the same character, this difference is 0. So that's why we have to add 1 to that. Right. And I think that is it. I'm not 100% sure. But yeah, we should try it out. So let's try this. Fingers crossed. Aha, so we made a mistake. We're not advancing the right pointer at any time. So we have to do that as well. So let's try again. And also, we're not advancing the left one. Oh man, making mistakes here. Okay, so that looks much better. Passing the test cases. Let's see if we also pass the real test. Ooh, yeah, okay, cool. So that's really nice. So that pattern, you need to remember. That's like one of the things. You just have to know it. And you have to spot when you want to use it. So we went from O of n squared and O of n time, O of n squared space and O of n time, O of n space to linear time and constant space in mere minutes, although it was probably several minutes. And yeah, so that's that. In an interview, I skipped it this time, the stepping through the code to spot any bugs. You always need to do this, obviously, otherwise you run into this, oh, something's wrong with my code, I need to fix it. And that's always a bad impression. And some companies, they punish you in their reviews. Like if you make those mistakes and you run your code and then you identify the mistakes, that's not good. If there's another candidate who doesn't do that and who's equally well in communication as you, of course that candidate is going to move ahead more likely than you. So yeah, pay close attention and also pay attention to when you advance the left and the right pointer. You don't want to advance the right pointer before the result, for example. Yeah, that's that. Thanks for watching and have fun implementing these 4 approaches. And try to do it without looking at my code. Just understand the code and then try to do it yourself from memory. That's the best practice.